So here's a few minutes on magnitudes and colors and filters. First, let's talk about magnitudes. So magnitudes is a funny unit. It's because it's a very old unit. So about 130 BC, a Greek astronomer by the name of Hipparchus made the first catalog that we know of the stars. And he called the brightest ones first magnitude and the faintest ones sixth magnitude. Some couple hundred years later, in 140 AD, Ptolemy copied this system, and then his books became the basic text for studying astronomy for the next 1400 years. So we're kind of stuck with the system. It is what it is. Faint ones are big numbers and bright ones are small numbers. So from that original system that was only defined between first and sixth magnitude, it's now extended in infinite range in both directions. So very, very, very faint things are 28th, 29th magnitude. Very, very bright things are -2, -5 magnitudes. So it's a very strange system. It is also a logarithmic system because it is based on the appearance of these stars to Hipparchus's human eye. And human eyes respond logarithmically. So a magnitude, by definition, by mathematical definition, is really a flux ratio. It's actually the log of the flux ratio. So here's the definition of magnitudes. The magnitude of object number 1 minus the magnitude of object number 2 is equal to 2.5 times the log base 10 of the ratio of flux from object 2 to flux from object 1. Note that 1 minus 2 is the ratio of 2 to 1. That's how you get the inversion, where brighter things have smaller numbers. Now, note that it's a log of the ratio of the fluxes. So when you have a difference in magnitudes, you have a ratio of the fluxes. So the magnitude system in the optical is all pinned on how bright a star called Vega is. Vega is one of the brightest stars in the sky, and Vega is defined by this system to be 0. So then you plug in Vega for object number 2. So you have M1 minus 0, because Vega is 0, magnitudes, is equal to 2.5 times the log of the flux of Vega over the flux of your object. So here it is. M is equal to 2.5 times the log of the flux of Vega divided by the flux of your object. So Vega is defined to be 0 magnitude. And so when you say that something has a magnitude of 6, that is an implicit comparison to Vega, because magnitudes are flux ratios. Now in the infrared it gets really complicated, because when they looked at Vega in the infrared with a satellite called IRAC, they discovered that in fact Vega doesn't look like you expect. It turns out Vega has a huge infrared excess because it has a bunch of dust around it. So it gets even more complicated because infrared magnitudes are therefore defined with respect to what Vega would be if it didn't have an excess. And that's really hard and opens the door for arguing about whose models are right. So calibration is tough. But at the end of the day, magnitudes are defined with respect to Vega. So just a reminder, stars, of course, get fainter when you put them further away. So the same star close up is bright, and the same star further away is faint. So apparent magnitudes, which are usually written with a little m, are the observed brightness. It's how bright the object appears to us to be from here. Absolute magnitudes is the brightness an object would have if it were at a standard distance of 10 parsecs. That's just arbitrarily defined. And a parsec is defined as 3.26 light years if you need that conversion. So the relationship between apparent and absolute magnitudes is given by apparent magnitude minus absolute magnitude is equal to 5 times the log of the distance minus 5. Little m is the apparent magnitude, big M is the absolute magnitude, and d is the distance in parsecs. Now, that means, if you look at that math, that further away things that are fainter have bigger numbers. So a star with a magnitude of 1 is brighter than a magnitude 6 star. But magnitudes are logarithmic by definition. So the magnitude of 1 is really very much brighter than a magnitude of 6. Not 6 times brighter, but 100 times brighter. So if you measure the magnitude of a star in any one band, implicitly you have a comparison to Vega. But if you measure the magnitude of a star, or anything else, in two different wavelength bands and compare them, the Vega flux cancels out. So you can do the math. Go back and get this equation here and write down magnitudes in V band is equal to 2.5 times the log of the flux of Vega in V band divided by the flux of your object in V band, and subtract from it the magnitude in I band equals 2 times the 2.5 times the log of the flux of Vega in I band divided by the flux of your object in I band. And you'll find that the Vega flux cancels out. So V minus I for the same object is 2.5 times the log of the ratio of the flux of your object in I divided by the flux of your object in V. So what do I mean by colors? V and I band, I just kind of threw in there. What does that mean? Okay, so we've been talking a little bit about filters, but what exactly do I mean when I say filters? Well, you can kind of think of them as these kinds of cellophane. This happens to be a gel from a theatrical company. And the reason we get the theatrical gels to do this demo is that they are pretty narrowly spaced in color. There's not a lot of leakage, in this case, beyond the red. So when you look at the world through the red gel, as soon as my camera auto balances, you will see that the world looks different. There are different things that are bright and different things that are faint. When you look at the world through green, different things are bright and different things are faint. When you look through blue, different things are bright and different things are faint. So I picked this necklace deliberately today because it has a variety of colors. Here's a bracelet, which I'm going to hold up in front of a white piece of paper so that you can see the colors pretty clearly. Let's look at this through red. There are things that appear to be black when you look through the red filter, and there are things that are bright when you look through the red filter. With green, which one do you think is going to be bright and which ones do you think are going to be black? Some of the colors are black and some of the colors seem white. Through blue, some of the colors are black and some are white. Well, let's look at them again. So we've got red on the top and purple on the bottom. Through the red filter, all of the red, orange, and yellow colors are white. They blend into the paper. But the blue, purple colors are black. Let's look through green. Now, it's not perfect, but the green is the brightest, and the red and the purple are the darkest. Now through blue, red is dark, and you start to see brighter colors in the blues. So it's not perfect, but it works better than you think it should. Here is a brightly colored, fake, squishy office plant. Let's look. Think about what it's going to look like when I put the red filter on. So the leaves look black, and the flower looks white. With green, now the leaves are bright, and the flower is black. And blue, the leaves are brightish, but still almost brown. Certainly not like they did. They certainly don't look like they looked through the green. And the flower is black. Here's my friend Kermit. In red, he doesn't look green at all, and his megaphone looks white. In green, he looks bright, and his megaphone looks black. In blue, his megaphone looks black, but he doesn't look nearly as bright as he did in the green. So colors in the astronomical definition is the difference of two magnitudes. Conventionally, it's a shorter wavelength band minus the longer wavelength band. And it is actually a ratio of fluxes. Okay, so in that demo, I can't do it as well within the PowerPoint universe, but here I have a bright red truck and a rainbow, and I'm going to put one of the pieces of red cellophane over it. Yeah, it doesn't work great, but ideally, in the ideal case, you have no purple or blue or green or yellow or orange light getting in. You just have red light getting in. So real filters are very different. So this is a real R-band filter from Kit Peak, and it shows how much light makes it through the filter as a function of wavelength. So things to realize here. It is not the idealized, this is called the top hat function. It's not the idealized top hat function from the prior page. It's trying, but it's not. Also note that none of it is completely transparent. There's always going to be light loss. So it's got a slope here, goes up pretty quick, and then there's bibbles and bubbles on the top, and then it's got a slope down, but look, it's got a long tail. And if you have an object that is very, very bright at 8,000 angstroms, that little bit of light that's coming through from something that's very, very bright at 8,000 angstroms is going to dominate over much less light coming from 6,000 or 7,000 angstroms. Because if you have something that's very bright here and very faint here, even that little bit of transmission is going to affect your measurement. So you can draw the band passes from any of a number of systems, and I have forgotten exactly where I've gotten this diagram, but you can, search Google on filter band passes and you can find a ton. So clear filters just let the light through. So U band is around 350 nanometers. Blue band is a little bit longer wavelength. R band, you see this one has a really horrible red light leak. That's an I band. It's got a pretty sharp top hat-like structure. V band in here is the green. You also have Sloan G, which is broad, Sloan R, which is broad, Sloan Z, which goes off the end of the plot here. You also have some narrow band filters. Those narrow band filters are much narrower in how much light as a function of wavelength they let in than these broadband filters. The narrow band filters let light just around, in this case, the H alpha emission band, in this case, a forbidden line of oxygen called O3. So those two bands are very important in astronomical observations, and so these narrow band filters just measure the light through those narrow range of wavelengths. So this is an actual picture of the Sloan camera, and that's so it's a huge array of CCDs, and they have the filter spread over it, and the way that Sloan operates is they basically let the sky slew past them. So their first row here is R, I, U, Z, and G band. So it's kind of hard to see because of the way that the light is scattered here, but on this last row you can see the I, U, and Z are pretty black, and the R is red and the G is green. Here's another view that I found off the web. This is a Sloan set of filters, and that's G, so it's kind of bluish. Even though you might think from the name G it means green, it's kind of bluish. U is a lot of ultraviolet, so it looks black. There's R, which looks like construction worker orange. Here you have Z band, which is into the near infrared, so it looks black. And you have I band, which in this view is really, really dark red. So that's consistent with what we were seeing over here, right? Because I don't have Sloan U on here, but it's over in the short wavelength. We can't really see it. Sloan G, Sloan R, Sloan I is somewhat like this I, and Sloan Z is out here. So it makes sense that we don't see anything other than black through Sloan U or Sloan Z, because they're reaching into regions of our vision where we don't see those wavelengths. So of course it looks like a black piece of plastic or glass. J, H, and K are near infrared bands, and they were developed originally for observations from the ground. So here I have transmission as a function of wavelength, and the black is what you get when your light goes through the atmosphere. You get all sorts of deep absorption bands from oxygen and carbon dioxide and water, and so they placed the locations of this J, H, and K system to take advantage of the windows in transmission that make it down to the ground. Now, the two-mass system is actually technically called K short rather than K. Original K went all the way out here, but I'm pretty sure this is a water band. So when there's varying amounts of humidity in the air when you're observing, that shape changes a lot during the night or from night to night. So K short cuts off before that absorption line kicks in, and so it's more robust against the amount of water you have in the atmosphere when you're observing. Here are transmission curves for the 4 WISE bands at 3.5, 4.5, 12, and 22 microns. Again, not top hats. They are pretty complicated. And so when you're doing detailed modeling of sources to figure out what magnitudes you expect, you have to take into account the fact that the 3.5 micron filter lets a lot less light through here than it does there, and the 22 micron filter lets a lot less light from here through than it does from there. The names of the filters come from the effective central wavelength, so it's weighted by the transmission, and it's quoted as 3.5 microns is the weighted average through that band. 4.5 microns is the weighted average through that band. 12 microns is the weighted average through that band, because see, there's more transmission here than there. 12 would be here, right? But it's not exactly in the middle. It's a weighted average. And then similarly, 22 microns is here. It's a weighted average over that whole bandpass. Here's some IRAC bandpasses. I have some stray models in there. It's just the figure I could find. So here's the 3.5, 4.5, 5.8, and 8 micron filters. You can see they're much closer to top hats than the WISE filters are. So this is just another way of thinking about it. This is more akin to the cellophane demo that I was talking about before. So this is technically reflection and not transmission, but so is the demo that we were looking at. So here's power as a function of wavelength, and what the author of this figure did is he's got some kind of a device that's designed for graphic designers so they can match colors exactly. So it's some kind of a machine that you put a color into, and it gives you a plot of exactly how much power is coming out as a function of wavelength so that you can match colors exactly. So you can see the white crayon, you might barely be able to see it there. The white crayon is kind of like the clear filter, right? It reflects light. The white crayon reflects light. The clear filter lets all bands through. We have a collection of reds here from his box of crayons, and you can see that all of them have a lot of red, and then they fall off through the greens, and they have very little purples. So the greens are, have some red in them, but they peak up here in a way that the reds just don't. And then they fall off when you get to the blues. So now we have a bunch of blues, very, very little red, and then they pick up in the blue. So it's the same idea. Here's another example. So I have a friend who used to work for the International Dark Sky Association, and there's apparently a very expensive but very cool toy you can buy for your iPhone that will take a spectrum of whatever it is that you look at. And my friend Scott got his hands on one of these toys, and he ran around taking spectra of everything he could find. Of course, he had it in the context of dark sky lighting. But once you have the toy, you can do whatever you want. So here is his plot of the emission of an orange lava lamp. Lots of orange, less red, very little yellow, green, blue, and purple. This is why he really had the toy, was because he wanted to take spectra of a low-pressure sodium light and a narrowband amber LED light to show that if you have low pressure sodium lamps that you want to replace with LEDs, you need to make sure you get the narrowband amber LEDs and not the bright white ones. So in the context, bringing it back to astronomy, it's often really useful to take the same object and compare its brightness at 2 different bands. And you make that comparison as a ratio of flux densities, in other words, a difference of magnitudes. So you take the bluer band minus the redder band, so B minus V, J minus K, V minus I. It's always bluer minus redder. And when you have established that convention, then whenever you are looking at a color, larger numbers are redder and smaller numbers are bluer. So remember, the difference of 2 magnitudes is actually a ratio of the fluxes, okay? So another way to wrap your head around this, imagine a hypothetical very red star. So your imaginary star is brighter in red than all the other colors of light. That star, whether it is really close to us or really far away, is still red. The overall brightness decreases when you put it further away, but how red it is doesn't matter whether it's close or far away. So the brightness of red light divided by the brightness of blue light from this object is not going to change, no matter how far away or close up it is. If the star is farther away, of course, it's fainter in both, but the ratio of intensities doesn't change with distance. What does change the ratio of brightnesses from red to the brightness in blue is the temperature of the object. Things get hotter when they get bluer. So, temperatures. Blackbodies. A blackbody is a really hideous looking but actually very elegant mathematical equation that idealizes the radiation that comes off of a thermal body. It actually describes the thermal radiation really, really well. Turns out you are a blackbody. So are the heating elements in your toaster. When you put the toast in and you hit toast, they start out black, but then they get deep, deep, deep red. And the warmer it gets, it moves through oranges into yellows, and eventually what our eyes see is white hot. It just means that it's warming up. So it's going from deep red through oranges and yellows. Okay? So we can approximate stars as black bodies. Stars are not really black bodies, but if you can fake it, okay. And if you've ever heard of a star being characterized by an effective temperature, that's what it means. If you fit the stellar emission with a black body, the temperature of that black body is the effective temperature of the star. Sometimes we can approximate dusty disks around these stars as a second or even third black body being added to the star. Now, remember that when we talk about SEDs, it's not the same as black bodies. SEDs is brightness or energy as a function of wavelength, spectral energy distribution. It can be fit by a black body function, or two or three all added together, but SED and black body are not the same thing. They're not interchangeable terms. So black bodies, if you plot intensity as a function of wavelength linearly, here you have something bright and blue, and as it cools, you get a peak that goes from past purple into green and then past red. Here's another representation of it where they've actually drawn a line to connect the peak values through all the black bodies of these different temperatures. Now, in the 1800s, when people were struggling to understand how this emission worked, there was somebody by the name of Wien who described the mathematical relationship of the short side of the curve, and Rayleigh and Jeans, two different people, mathematically described this side of the curve. And it took a little while for them to, everybody to combine it into one mathematical expression. But if you plot, I plotted a black body here in a log scale, so log of brightness and log of wavelength, so it has a little bit different shape than that. But on the short wavelength side, we call it the Wien side. On the long wavelength side, we call it the Rayleigh-Jeans side. So here I have a movie. So here I've got plotted energy as a function of wavelength. And there's the black body. And it's going to start at a temperature of 2640 Kelvin, which is the temperature you expect for an M8 star. An M8 effective temperature is 2640 Kelvin. So I'm going to start the movie, and I'm going to heat up my black body. So I'm through the M's, now I'm into the K's. The whole thing is getting brighter, and the peak is moving bluer. Bluer and bluer and bluer. Okay? Now these completely illegible labels down here say UBVRI, because those are typical optical bands. And the I has a vertical line. Then we've got JH and K, no lines, near infrared. We've got the 4 bands from IRAC on Spitzer, 3.5, 4.5, 5.8, and 8 microns. Then we have MIPS, 24, 70, and 160 microns. So when this movie plays, you can see that there's very little change through the infrared bands. The whole thing is getting brighter. It's moving up and moving up and moving up and moving up. And when the temperature starts to turn around and cool off, you'll see it come back down. So the overall brightness changes, but the slope does not. The Rayleigh-Jeans side of that curve always stays the same slope. And that is critical for understanding infrared colors. The ratio of the fluxes at these bands does not change as the temperature is changing for a black body. However, if you look in the optical, The optical ratio of fluxes changes rapidly through these temperatures because you have the peak of the black body moving right through the regime where we have optical colors. So if you look, see the peak is moving rapidly through as the temperature changes the optical color bands here. And that is why you can take a ratio of the fluxes or a difference in magnitude, say B band minus V band. You can tie B minus V colors really easily to temperature because the peak of the black body is moving through those bands. So the ratio of the fluxes as a function of temperature in the optical bands changes rapidly. And that's why that works. But in the infrared, it's not changing. So when we find infrared colors, the ratio of infrared fluxes to be not 0 for a star, we know that something interesting is going on. So you may have heard of a Hertzsprung-Russell diagram. It's usually presented in textbooks as luminosity as a function of temperature. But when they discovered it, it was the observed absolute magnitude as a function of not spectral class so much as B minus V. So you know that hot things are on the left, cold things on the right. Blue colors are on the left, red colors are on the right. O stars are on the left, M stars are on the right. Bright things are at the top, faint things are at the bottom. Remember, the magnitude scale has small V magnitudes at the top and large V magnitudes at the bottom. So if you go to plot this, say in Excel, you're going to have to convince Excel to plot it with the large numbers on the bottom. Now remember, because B minus V can easily be converted to temperature, you can make this mapping between B minus V and temperature really easily. So HR diagram, technically as it's defined, is in theoretical space, the luminosity and effective temperature. But when we go out and actually take data, we're measuring brightness and color, say V and B minus V, and we place things on the diagram. So an HR diagram really is something called a color magnitude diagram. It's got the color on the x-axis and the magnitude on the y-axis. And because of all the work that has been invested in understanding the astrophysics that is encompassed in an HR diagram, you now know, we as a society, we as researchers know that things in certain regions of the diagram are now known to be very specific kinds of stars. So if we go to this HR diagram and I gave you a new object and said, well, it fell down here, you would say, oh, well, that's a white dwarf. If I give you a new object and put it up and say, what is it? It's over here. You can say, well, it's a red giant. So you have now understanding about the nature of a new object once you understand where it gets placed on this color magnitude diagram. The thing is that is a stylized HR diagram, and reality is messier. So that's the cartoon version. This is closer to real data, closer to reality. These are all Hipparcos stars, and so we know that they're all stars, and we know what their distances are because they come from the satellite called Hipparcos that measured parallax, and so they can get the true distance to these objects. So we can correct their observed magnitude to the absolute V magnitude. Remember 5 log D minus 5 from before? So what we have here then is a variety of B minus V colors and absolute V magnitude, in other words, brightnesses. And there's the main sequence. There's the giant branch, right? And so there's clumps and texture in this that tells you something about the objects that are plotted here. And so if I give you a new object and tell you where it falls in this diagram, you can learn something about it by figuring out where it falls in the diagram. Young stars are even more complicated because young stars are not yet on the main sequence. So all the young stars will be when you're in the same cluster, it will be about the same distance. So distance should not normally be a huge factor. Sometimes it is if the star forming region is elongated along the line of sight. But assuming that they're about at the same distance, you then have to worry about how old the stars are, as well as how massive. So when the cluster is around 10 to the 4 years old, all of the stars will be here. So the 15 solar masses, the 9 solar mass guys will be well on their way, chugging along to the main sequence, but all of the low mass stars will still be condensing. By 10 to the 5th years, you have 5 solar masses, 9 and 15 cruising over to the main sequence, and the lower mass stars are starting to heat up as they're collapsing. Now, they go vertically in this diagram as they're continuing to collapse, and then as soon as things start to get serious, they start to burn deuterium, they start to rearrange their structure a little bit. They don't ignite hydrogen until they're on the main sequence, but all those bumps and wiggles come from various structural changes as the thing is condensing, and when convection starts and when deuterium gets burned, all those wiggles there are deuterium burning. So lots of physics that goes into these models. But the punchline here is that the young stars are going to be above the main sequence because they're young. So this is reality again. This is fields in Orion where I've just plotted everything. So I band versus V minus I, so brightness as a function of color. And you see there's a condensation of stars that are there. And you have a condensation of stars down here. All of this condensation are likely to be at the same distance there in Orion. These are field stars. They're just things that happen to be in the field of view. So here's another view of the same fields. There's the condensation, that's Orion, and these are all stars from the field. This is the zero-age main sequence. In other words, where those stars here will end up when they finally ignite hydrogen. So again, just to wrap it up a little bit, infrared colors are going to tell you something totally different than the optical colors. Because B minus V, or for that matter V minus I, or a lot of other color combinations, covers the peak of the blackbody curve, and so they change rapidly when temperature changes. But because the IR colors are pretty much all on the Rayleigh gene side, except for very, very cool stars, the slope is never going to change. So the ratio of IR fluxes or the IR colors are never going to change. So the IR colors are going to tell you about things that don't look like blackbody curves. And that's good because young stars don't look like blackbody curves.